Sorry. All right. So we are live. Good morning and welcome everyone. So today we are going to talk about simplex algorithm and its roots, and the important part of it is grounded on this theorem 3.10. And let me just, before we go to this 3.10 in detail, so let me just gently guide you to this. So you remember that we were looking for basic solutions of the problem, right? So let's just write the problem in a situation where we are looking for minimization of C transpose X under the constraint that AX is equal to B. So this is what we are talking about. This is what we're talking about, and I'm not writing the positivity or the non-negativity constraint here, but we assume that all the components are non-negative. So if they're zero, they cannot be smaller than zero. And we are looking at a basic feasible solution, or and basic feasible solution means that we have some zeros in it and then some basic variables which are non-zero. So I'm going to write this like this, that A is now partitioned into the basic part, and then the null part meaning that those particular components of the solution vector are set to zero, and those indices which are in this B part, those indices are possibly non-zero. And we have this solution, let's call it X for now. So X is just XB, and then the null part consists of all zeros. So right, so the indices of this X vector that correspond to these which are in this B matrix part, those same indices here may be non-zero, but the ones that correspond to this N part here, those are set to zero. And I'm writing this so that those indices are first, but they can be any indices, and we can just think of this as being the matrix being rearranged. And now let's see what happens when we move a little bit in some direction from this X. So let's look at the point where we are moving from X to X plus delta X. So I'm looking at the cost is C transpose X plus delta X, right? So I moved from X a little bit. So I added delta X. So that's a little bit of a perturbation or a little bit of change from X. And the constraint is still enforced, so that AX plus delta X is equal to B, right? This must be true because the constraints hold. So AX plus delta X, that must be equal to B because it's still feasible. Remember, we are only moving in a direction where we're still allowed to move in the feasible region. So it follows from this fact that because AX is B and A times X plus delta X is B, that A times delta X is in fact zero. Because if we are moving from into the direction of delta X, then A times delta X must be zero, right? So as long as we're moving from X to X plus delta X in such a way that A times delta X is zero, then A times X plus delta X will still be B, all right? What is more, because A times delta X is zero, so let's split this delta X into two parts, and it's delta X B. How do the components in the B part change? But then there may be delta Xn, right? So I'm rewriting simply this vector X delta X as this, the change that occurs in the basic variables, and then there's the change that occurs in those variables that were zero. So they're no longer zero because we are moving from one point to the next. And the change in the cost, so cost change is of obviously C transpose delta X, right? Because I mean, we moved from C transpose X, C transpose X to C transpose times X plus delta X. So the change in the cost is C transpose delta X. So what the theorem aims to say, and I'm going to shortly show you how that happens, is that if this cost change in all the possible directions to which we can move is always greater than or equal to 0, then we are at an optimal point. It simply means that if we can prove that this cost change is always non-negative, so we can only increase or at the best stay the same, then we have found the optimal solution to this optimization problem. I mean, really, I mean, we're talking about linear, which is a convex problem. We found a point from which we can not move to any direction where the function's value gets smaller. Then because of convexity, this means that this is obviously a optimum point, okay? So the cost change must be this. And if the cost change is always positive, then we know that it's an optimal point. So let's look at what happens to this cost change. So we rewrite this that a times delta X must be equal to 0, right? So I'm going to rewrite this as there's the B part. So B times delta XB plus N times delta XN must be equal to 0. So we must have this, because delta A times delta X is 0, and now I've split this A into these two parts, the B part and the N part. The sum in this must be 0, right? So you're still game, right? And we rearrange now this equation because B is an invertible matrix. We can look at this what happens to delta XB, right? And what happens to delta XN. We can express this delta XB in terms of this delta XN. And remember, delta XB are the ones that changes in the ones that were currently positive, and delta XN is the ones that change in the ones that were currently 0, right? So the delta XN here, it must be positive or at least non-negative. So while these XB variables are now positive, they can go down. The delta XB may be negative, but the delta XN cannot be negative, because otherwise we would go into the zeros would become negative, and that's not possible, right? So let's look at this. And what happens then is that we'll just look at this, we'll just rewrite this as delta XB is equal to minus the inverse of B times N times X, delta XN, right? So I just multiply this with inverse of B, and then I just move this other thing on the left-hand side. So we have here this. So let's look at the cost change. What happens to the cost change? So there is the, I had here the cost change. So I'll rewrite this cost change a little bit. So I'll write this as C transpose, Cn transpose delta Xn plus Cb transpose delta Xb, right? I'll rewrite it like this. I'll rewrite it like this. And now I'll slip in this this delta XB. So what I will have now here is Cb transpose B inverse N delta X N, and in the negative plus Cn transpose delta X N, right? So I have this. This is what I have. And I'll just take the delta Xn as a coefficient here. So I get here, rearranging this, I get Cn transpose minus CB transpose B inverse N. That is our cost part times delta XN. So I have this. Now, recall, when we are moving from this point, the delta XB may be negative, but the delta XN must be non-negative. So these can only increase. And if all the components of this cost vector, so what does this cost vector here do? It tells us how does the cost change when we are going to increase these components, the ones that were zero. So this amounts to the net cost of the change when we are increasing those variables that were zero. And this takes into account the fact that when we are increasing those variables that were zero, some of the variables that were non-zero will need to go down, right? And this takes into account for that. So the so-called reduced cost vector here, the C hat and transpose, it tells us each component of this is a very specific interpretation. It tells us that the particular component here that was zero, the variable that was zero, when we increase that and that alone, then the total cost, and now because we have to also change the basic vectors, because we have to, when we are increasing one of those variables that were zero, then some of the basic variables need to go down, or maybe some of them go up as well. We don't know, they go up or down depending on the matrix. And this reduced cost vector 3.7 tells us component by component what happens if we just a little bit nudge that zero variable upwards. And if all of these are greater than or equal to zero, then there are no variables that are now zero that we can increase and make the cost smaller. And that's what this says. All right. I'm going to stop the recording for a little while. Let's do a little bit of a so the whole thing was here defined as the so-called reduced costs, the elements of the C hat n vector. And the point of this C hat n vector is that it's basically, if you look at this last just before the black square, you look at this last equation, it's just that if by theta is a small change in the direction into which you go, then the cost change is Zx, which is the original cost at x, plus theta times this C hat n. And this is component wise, the component S is being changed. And this means that the cost if there's a negative cost involved there, then the cost will go down. So X is not optimal if there's a negative cost in this reduced cost vector. If one of the components is negative, then we can make the cost smaller by at least a little bit. So it means that it's not optimal if the C hat n is has a negative component in it. If we have a basic feasible solution, then if we look at what follows from this theorem is that if we have a basic feasible solution, so that we have these B variables, which are not necessarily zero, we have these N variables, which are zero, and we have the corresponding reduced costs. Then there are two possibilities if the reduced cost vector has a component that is is negative, meaning that there is a non-basic variable such that by increasing that we can decrease the total cost. Then two possibilities exist. One, the optimization problem does not have a finite solution, in which case we say that the problem is unbounded. But when we say that it does not have a finite solution, it means that it is possible sometimes to find a direction, meaning find a positive a vector that is in the null space of A, meaning that you can move in that direction without violating that AX equal B, so that A times delta X, that delta X is that vector, A times delta X is 0. And it's all its components are positive, and the net effect on the cost is negative. It means that if you can go into that direction without ever reaching the situation where one of the variables becomes negative, then you can just make the cost infinitely small. And in this case, we say that the linear programming problem is unbounded. That's one possibility. The other possibility is that one of those components in that delta X direction into which we go will be negative. It means that we can go into that direction until such a time as some of the other one or more of the other variables hit 0 when you increase the one of the null variables. Because their corresponding reduced cost component is negative, it means the cost will go down if we go in that direction. It will go down until such a time as one of the basic variables hits 0, in which case we found a new basic solution. And because the new basic solution has a smaller cost than the original point, then we found a better point. So really, when we are dealing with a basic feasible solution, we now have three options that happen. One of three things happens. One, the conditions in theorem 3.10 are met. We calculate the reduced cost by simple linear algebra. It only involves the basic part of the matrix, taking the inverse of that, looking at the cost vector and looking at the null part. So these are all, everything that is calculated in 3.7 are done straightforwardly by rearranging the matrix, doing a couple of matrix multiplications and one inverse, and then multiplying by the cost vector. And if the resulting vector has only positive components, then we are dealing with the optimum point. 2, if it turns out that when we go into, we find a direction to which we can go infinitely far without any variable becoming negative, and the corresponding cost, corresponding reduced cost component is negative, it means that the the cost function can be made infinitely small. It's unbounded, and we can stop. We don't have to worry about it. The problem hasn't got any solutions. Or 3, we find a direction in which the reduced cost is negative, but when we go into that direction, then one of the basic variables becomes 0 or has a threat to become negative, and we stop and we have a new basic solution. So this gives us really the algorithm. The algorithm is based on doing one of these 3 things. Not going to go through the proof. It's fairly simple to look at this. So I just very quick glance at it. So in the first case, if we pick the variable S, and this theta is now the how much we go in that direction, then the cost becomes smaller when we move to point Y, which is x plus this theta ES, meaning that the increase in variable S, and then obviously B part has to change accordingly by this B inverse A. And we go into that direction, and if it's feasible for, regardless of how far we go in that direction, we can make the cost infinitely small. So the cost approaches minus infinity when theta goes to infinity, and we can go that way. So that's one possibility. The second possibility is that we find one of the components in the basic vectors, so that when we increase s, the component s, which was 0, we increase it by theta, then we look at, 3.9 just says we find the one that first goes to 0. That's the minimum of the quotient. So the a hat s, if you look at that in the upper part, the a hat s is b inverse a hat s star is basically the change in the basic variables. So that's b inverse times a hat s. So we move by theta times a hat star. And then we look at the component-wise, that incurs a net effect on the basic variables. So we look at 3.9 means that we are looking at each variable, j, and this a hat star is the net effect on that variable. We look at this quotient here, really at 3.9. It's just we look at which one of the variables is the first to hit 0 when we adjust them for the change in, we're increasing variable s, and the basic variables are adjusted accordingly. That's the b inverse a hat s. And then we look at which one of those variables is the first to hit 0. That's your 3.9. And that's as far as we can go. When we go that far, then one of the basic variables hits 0, and we have a new basic solution. It is better than the original because the corresponding reduced cost component is negative. So that's how much it changes. And we have a new basic solution. So here is the simplex algorithm. It's got only one problematic part here, which is not explained how you do it. But once you do that, once you get started, then the algorithm is relatively simple to run. So firstly, find a feasible basis. So this is the tall order here. Finding a feasible basis is not immediately obvious because, if you look at the columns of the A matrix, you can think of the A matrix as being wide, but not very high. So it's got a lot of columns and not that many rows. You have to pick some subset of the columns to make for a non-singular matrix, right? And then the corresponding non-singular matrix inverse times B is the constraint vector, should have a solution. Well, it always has a solution, but it should have a solution where all the components are non-negative. And if you can't find that, if you can't find that, then there is a problem. But if you can find that, you get to this point 1, choose a feasible basis. So once you have one feasible basic solution, the rest is kind of like walk in the park. If we have a current feasible basis, we have this xb, which is gotten from the equation bxb is equal to b. We compute the corresponding reduced cost as per theorem 3.10. That gives us component-wise, the net effect of those variables increasing that are currently 0. If all of those reduced cost components are non-negative, then we stop. The current basic solution is optimal, and xb, or this x that we have currently, is the optimum solution. We can stop. If not, we find an index that has a corresponding negative reduced cost. It means that we find one of those variables that are now 0, so that the net effect of increasing that variable is negative on the cost. So the cost goes down if we increase one of those 0 variables. We pick the corresponding column of this n, the null part. That's your change, because think about the A matrix here. Here's one column of it, and this corresponding variable is being increased, right? So this is how AX changes when we move this. So you have to incur a corresponding change in the basic variables. That's you gain that by multiplying this column by the inverse of the B part, right? That's in your part 5. So if you do this change and then the inverse of B times this vector, then that is the net change which keeps AX equal to B, even if we increase this variable. If the net effect is negative, and now remember, we are going, this negative means here, it's because we are multiplying this with the inverse of B, subtracting this from the basic variables. So if this has only negative components and we're going to be subtracting this from the basic variables, it means that if we go in this direction, the basic variables all increase. So if all the corresponding components of this A star hat are negative or non-negative, it means the problem is unbounded because we found a direction so that we can increase this variable up to even infinity, all the while making the cost smaller and smaller. So that's why the problem is unbounded if all the components of this A star S are non-positive. If it has a positive coefficient, because we're going to be subtracting from our basic vector this A star S, or some multiple thereof, we look at the components. We look at the components of the basic part and look at the ratio of this change for each component. And where the ratio is smallest, it means that we can go this far. The ratio tells us how far we can go before the corresponding B variable hits 0. Okay, obviously some of these will be increases, but if they're meaning that this ratio is negative, because remember we're subtracting, so the sign is different. So but we look at the smallest positive quotient here, and we pick that variable. Let's call that R. It means that when we move in this direction, this is the increasing null variable that was 0. Now we're increasing this, and there's a net change in corresponding net change in the B variables. Then R will be the one that, let's say it's this one, this goes to 0 first. So we switch that R and the S. So S becomes the new basic variable and R becomes the new null variable. And we start again. We calculate the basic solution, we calculate the reduced cost and so forth. Here's an example of it. So we solve this problem with the simplex method. We do this one by one. I'll go through this with you, and then I ask you to review this in groups after I've done this. So we start with the minimization of two variable problem. Variables are positive. They've got negative coefficients, and the constraints are that 2x1 plus 3x2 smaller than or equal to 6 minus x1 plus x2 smaller than or equal to 1, both being positive. We have to add slack variables now to make this into the standard form so that these become equalities. We add x3 to the first one and x4 to the second one. So we get this A matrix becomes 2, 3, 1, 0, minus 1, 1, 0, 1. Here is our solution, our problem now in matrix format, and we start with calculating this, solving this with the simplex method. So we need to find a feasible basic solution. We notice that the last two columns form an identity matrix, and because all the variables all the components of B are positive, we can choose the third and the fourth variable as our basic variables. So we choose as our B matrix the one that has the last two columns, 1 and 0, and then 0 and 1. So this is our B. It now consists of N, the identity matrix. The N is formed from the first two columns. So that's the original matrix before adding the slack variables. It is actually often the case that when we add slack variables, we end up with this as our starting point. Now we set we find the basic solution. It amounts to x3 being 6 and x4 being 1. These are the basic variables. And obviously x1 and x2 are 0 because these are the null variables. The cost vector part on the basic part is zeros because these were slack variables. And then the null part, that's negatives. Now we calculate the reduced costs, and because of the simplicity of the B matrix, we get that we're actually left with only the Cn part because the cost B, CB is zeros. Then we see that the net effect of increasing x1 by 1 unit is a net effect of -1 in the cost, and the cost of increasing x2 by 1 is a net effect of decrease by 3 units in the cost function. This is the reduced cost situation. So as a heuristic, it doesn't really matter in the grand scheme of things. From the point of view of finding the optimum, there is no reason, a priori reason for us to choose one or the other, but often a very good heuristic is to pick the one variable that has the smallest reduced cost, so the most negative. The most negative cost comes from increasing variable 2. Now, if we increase variable 2, then every unit increase in variable 2 means corresponding decrease of 3 units in the cost. So we pick the second variable. This means S is now 2. That's our index. It's the variable number 2. We look at the corresponding column in the matrix A, and that's the column 3 and 1. So it means that if we increase the value of this second variable by 1 unit, then the first row net value will increase by 3, and the second row net value will increase by 1. It means that the constraint would be violated by 3 units in B1 and 1 unit in B2 if we did nothing else. So we need to incur a corresponding change in the basic variables. So that's we do with A2 star hat by multiplying this A2 hat by B inverse. That means that this is how much the basic variables, which were 3 and 4, need to change. And the corresponding changes in the basic variables need to be that we need to change, whenever we increase S, the variable 2 by 1, then we need to do the corresponding decrease by 3 units in a variable 3, which is the first basic variable, and 1 unit in variable 4, which is the second basic variable. Now we calculate which one of these is going to hit 0 first. So the third variable, which had value 6 and will decrease by 3 units for every unit increase in variable 2, it can take 2 units increase in S, whilst the second basic variable, which is variable 4, which had value 1, will incur a decrease of value 1, but for every unit of increase in variable 2. So it's going to hit 0 after 1 unit increase of variable 2. So we choose the second one, meaning the one with the smallest ratio, because that's the one that's going to be 0 first. So it's going to be 0 when we increase this variable 2 by 1 unit. So we switch R, the second basic variable, with S, the second null variable. So our new basic variables will be 2 and 3, and our new null variables will be 1 and 4. Right? And we know by now that, in fact, this new basic variable, which is number 2, will actually, because we know that it can increase by 1 before the corresponding variable goes to 0. So we know that it's going to get the value 1. So we calculate the new basis, which consists of variables 3 and 2. We calculate pick the corresponding columns to this B matrix, and N now has 1 and 4. We pick the corresponding columns to this N matrix. We calculate the new basic solution, and it's going to be 3, 1. I could have told you this from here, because the ratio is 2 for every 1 unit, and for the other one it's 1 for every 1 unit. So it's going to decrease by a factor of 2. So the first one, when the second old basic variable becomes 0, the second one will be half of what it was, because the ratio is 2. So it's going to be 3. So we have a new basic solution consists of the vector 3, 1, meaning x3 is 3 and x2 is 1. Obviously, the null variables will be 0. We calculate the reduced costs, and we notice that there is one component that corresponds to negative, and that would be the first null variable, which is the first variable number x1. We do the same thing over again. We calculate the net effect on the basic variables. This would be the A star 1 hat, and the net effects are 5 and -1. So this means that when we are increasing the variable 1, then the basic variable x3 will decrease by 5 for every unit, and while this second basic variable x2 will increase by 1 for every unit. And because that will increase, we won't make that one as our new null variable, because going in this direction won't make it 0. So we choose as our basic variable, obviously, the x1, and as our null variable, we pick x3. We switch those, and we have this new basic variables will be a1 and a2. Sorry, variables 1 and 2, x1 and x2. The corresponding B will have the columns 1 and 2, and the null part will consist of this 1, 0, 0, 1. We calculate this new basic solution, which is some fractional vector, 1/5 times 3 and 8. Null part obviously being null. We calculate the reduced costs, all of which are positive, and we conclude that this XB is our solution. So the solution is x1 is 3/5, x2 is 8/5, x3, x4 equal to 0. And we can calculate the optimal cost at -27/5. So this is really how it goes. This is how simplex algorithm works. There are other possibilities. There may be a situation where it becomes unbounded. There may be a situation where we find that it has no solution whatsoever, because it is possible. Yeah. So let's have a little break here. Don't have time. So we're back at this issue. We talked about and looked at this example here. I think we've learned what we have to learn from this example. We'll look at more examples in the exercises. In here, it was mentioned that when I look at the algorithm here, the part one, choose a feasible basis. So this is the tricky part, that is not always immediately obvious how to do this, because if you're choosing a feasible basis, it's not enough to choose a basis. It has to be feasible in the sense that these variables that you pick in the basis should yield a solution where all the variables are positive or non-negative in the solution. Because if there are negative variables in the solution, then this ratio thing doesn't work. We are in an infeasible region, and we should be aiming to find a feasible solution. But if we are in the infeasible region, in a region where some of the variables are negative, then this cannot be really adapted to work in that region. So we need to first discuss that how we find this. First need to discuss how we find the feasible basis. Now, it is very usual, very common, that all these problems are of the form ax smaller than or equal to b, where b is non-negative. That is very common to have the original problem constraints in this format, because very often the case is such that these constraints are resource constraints or budget constraints or something like this, and or time constraints or whatever. And the b vector is positive, so we have some resources, and then each line corresponds to resources consumed by something that needs to be done or something like this, that depends on the choice of x's. And then you're minimizing the cost with respect to things that satisfy those constraints. If we are in this lucky situation where the b vector is non-negative and all the constraints are of the form a1x is smaller than or equal to b, then in fact the constraint matrix becomes a1 and I, where I is the identity matrix, and then there are the slack variables, because for each of the rows there's a new column introduced with a corresponding coefficient equal to 1, other slack variables having a coefficient 0. So the matrix will look like this, that there is the original constraint matrix, then there is an identity matrix padded in the end, and then the variables will be the original variables and then the slack variables, and this should be equal to b. So we can take as our initial basic solution as being the identity matrix at the very end. This really corresponds to the original problem variables starting at the origin. If you think about it, we have a problem a1x smaller than or equal to b, and then minimize the cost function. So this, if you think about some other methods by which we would solve this problem, we could start from setting all x's to 0. Obviously, a1x is smaller than or equal to b if b is non-negative. If all x's are set to 0, then a1x is 0, and this is obviously a feasible point with respect to these original constraints. And then the slack variables simply say that there is as much slack as originally was possible, maximum slack, if you will. And then we can start from there. We can start from there to proceed to find the optimum solution. In this case, the initial feasible basis is easy to find. So it's just the B vector, right? For the slack variables, all the other vectors being 0. In general, obviously, this is not always the case. Sometimes we already have equality constraints. Sometimes we have greater than or equal to constraints, in which case the matrix at the end, the padded matrix, has negative coefficients. And unless the corresponding B coefficient is negative, then we have precious little we can do about that. So, in general, we can generalize from this by some method of artificial variables. I'm not going to go there in general, but let's look at two artificial, well, one artificial method, variable method, and the other one is kind of like a quasi-artificial variable method. In both, we employ variables that are not actually part of the model. Instead, they are just there to facilitate finding a feasible basis. So one way is to extend this, extending this set of variables. And first of all, what we do here is we can have, when it's in equality form, we can always make sure that the B variables are positive or non-negative. We can do this if there is a negative B, we can just take the corresponding row and then just take the negative of everything. Just multiply everything on that row by -1, including the B variable. Then that becomes a positive variable. I mean, equality holds. I mean, if there's some Z on the left-hand side and X on the right-hand side, then just multiplying both sides by -1, you know, it's still an equality that is true exactly in the same situation. So we can always make this equality form constraints into such that this B vector is non-negative. Now, the idea is that we introduce what are called artificial variables, one for each row. This has no effect on anything. You know, it's just that, you know, AX is equal to B, and then we add this identity matrix AI at the end, and this new variables Y, such that we add this IY into this. So, and let that be equal to B. Obviously, if this has a solution, then it has a solution in such a way that all the Y variables are 0. And in the big M method, what we do here is we then introduce these into the cost function as having very large positive coefficients. So we kind of we're trying to minimize the original cost function, and we're really interested in the X that minimizes it. So we take this Y, which are the artificial variables, and we make a very high cost in having non-zero Y. And if this M is very, very large, let's say it's larger than the largest positive coefficient in C times the number of variables in C as well, times the 1 over the smallest variable value in A, or something like this. We can guarantee that if we pick a large enough M, hence the word big M method, the large enough multiplier for these variables Y, then minimizing this cost, which has the original cost C transpose X, and then this capital M times Y, then minimizing this will will only occur in such a way that this Y will be 0. If it's non-zero, then the cost will be far larger. So if M is large enough, then what happens is that if this original problem does have any feasible solutions, then the artificially constructed problem will only have variables Y at equal to 0. If we have a basic solution of this 3.10, well, 3.10 has a basic solution where all the Y's are 0, so none of the Y's are basic solution in the basis if the original problem has some solution. Because If it doesn't, obviously, if the original problem doesn't have a solution, then this transformed solution always has one. So it's where we set this y equal to this b vector, and it's obviously that it solves this problem, but it has a very high cost, this capital M times basically b, which is positive. So it's a very large cost if M is very large. And if the original problem has a feasible solution, if we've chosen a big enough M, big M, then this is definitely not an optimal solution to this original problem, because in the original problem, we just added these dummy variables, these y's, and make them very expensive. Then they should vanish from the problem if we're solving it. If we solve 3.10, this artificially augmented problem, and find a solution that has no artificial variables, then obviously it is an optimal solution also to the original problem. And if the optimal solution to this 3.10 does contain these artificial variables, then the original problem doesn't have any feasible solutions. Also, as it stands, given that B is positive, so if the original problem is unbounded, meaning that it can go to minus infinity, then so will the problem 3.10 go to minus infinity if the original will go to minus infinity. That's not mentioned here, but it is the case. One of the problems in this big M method is that there is no way of telling how big an M can be solved, so that the artificial variables are by necessity eliminated from the basis. And having a very, very huge M, if you're using floating point arithmetic, a huge M will result in inaccuracies that may cloud the original problem a little bit. But it's a way to solve this. And other one is the so-called two-phase method, not two-phase, but phase as in two-stage method, if you will. So the problem of the two-phase method is similar to this big M method, in which we use also artificial variables. In this situation, we introduce these artificial variables, but we change the cost function in such a way that we assume that the original problem, original variables have no costs, and then each of these artificial variables has a unit cost. Now we know for a fact that we can have a feasible solution where this y is equal to this vector b, and we solve this with a simplex method. And if we solve it in such a way that it has zero cost, then that point, while not the solution to the original problem per se, is a basic feasible solution of the original problem, because it's a basic solution to a problem where all the y variables are zero. However, if such a solution does not exist, if we cannot find such a solution, then the original problem hasn't got a feasible solution, and you know, it's a moot point. So phase one, solve this one where we basically ignore or set to zero the cost of the original variables, and then these artificial variables have positive cost. Solve this problem. If we find a point X, then that is a basic feasible solution to the original. If we don't find a point X, meaning that if we solve 3.11 and it contains these y variables, then we cannot find, there is no feasible solution to begin with for the original problem. So I've usually said that if you study one of these, the two-phase or the big M method, and try to understand how and why do they guarantee that we can use them to find a basic feasible solution or even optimal solution to the original problem. And study these, one of them will do. I will ask in the exam, I will ask, you know, if you have no obvious basic feasible solution of the original problem, how would you go about searching? Then, cite either the big M method or the two-phase method. It doesn't matter which you choose. Look at these and study them and understand how they work, how they can be used to generate a basic feasible solution or a solution to the original simplex algorithm, in the sense that the original simplex algorithm doesn't get started without getting one of the basic feasible solutions. So these solve that problem, the big M method and two-phase method, both in their own way, different ways. You don't have to learn them both, learn one. But you can, of course, learn them both, because they both have ups and downs. But we're not going to be using too much time on this. Just understand that there is a way to kind of seed the problem in the way that because we need a basic feasible solution from which we start, then these are methods by which we can do that. Here are some examples, but I'm going to skip them for now. There are example M files for doing that. And we'll talk about duality on Thursday. So I'm going to stop the recording now. Oh, there was a message there. The question was, there was no guarantee of convergence. I think the original question was guarantee of convergence of the simplex method. That's actually a good question. The simplex method has a guaranteed convergence if the problem has a solution. Obviously, the problem may not have a solution, but if it doesn't have a solution, then there are two possible reasons why it doesn't have a solution. One, it has no basic feasible solution. And let's go look at this. If it has no basic feasible solution, no feasible basis, then we won't even get started with the simplex method. To detect that, you can use either the big M or the two-phase method, and notice that, yeah, all right, the original doesn't have a basic feasible solution. The conditions are found there. But if we have a basic feasible solution that we have found, and we start with the simplex method, then the result can be one of two things. One, we determine that the problem is unbounded. If the problem is unbounded, then there can be, of course, no convergence, in the sense that the problem doesn't have a solution. The problem has infinite number of smaller and smaller costs for a sequence. We can find a sequence of points where we go to infinity, and the cost goes to minus infinity. So that's a situation of unboundedness. It means that the problem cannot be solved in a way that, this is the minimum point, because there is no minimum. That's not really, there is convergence in the sense that we detect that this is what is happening. There is obviously no convergence because there is no solution. And if there is no solution, then no algorithm can obviously produce such a solution. However, if there is a solution, then the simplex algorithm will find the solution, and it will be found at stage 4, where the reduced costs are non-positive. Non-negative. However, there is one caveat here. One caveat here is that this, technically speaking, we are assuming that the basic feasible solution is not degenerate, meaning that none of the basic variables are 0. Degeneracy produces a problem for this stage 7, because if we have degeneracy, then the stage 7 results in a problem. If the corresponding net change of A is negative, or sorry, positive, I mean the A star S component is positive, and the corresponding X is 0, then we cannot actually bring this variable into the basis, because there is already an incurred net change in one of the variables, and that is already at 0. So we can't introduce this into the basis. So this provides a complication, and as such, just simply given like this. If there is degeneracy, we have to do something else. Now, degenerate solutions result in certain problems because we have to try another possible basis solution. And that is something that, strictly speaking, when you ask, does this converge? As such, without taking into consideration the degeneracy problem, and if there is a degenerate solution, then as it stands, this will not converge. But if we assume that there are no degenerate solutions, so no matter what basis you choose, it has no zeros in it, then this will converge. But even if there is a degeneracy, we can do things to alleviate the degeneracy. We'll talk about that a little bit, but for now, we'll just assume that there is no degeneracy. So sad to say, this is another complete treatise on the simplex algorithm. The degeneracy problem is real, but it's uncommon. Let's say it's uncommon. And in our examples, I'll try to make sure that degeneracy doesn't happen. All right, I hope this answers the question. I'm going to stop the recording now.